universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello, everybody, and welcome to Sky Tour Radio. I'm your host, Mark D'Antonio, and over here we have Tara Dialis. Hi, Tara. How are you?
Hi, everybody. Good to see you.
Down below here, we actually have Daryl Mason. Hi, Daryl. What's going on down there?
Hello, Mark. Trying to figure things out.
Excellent. Excellent. We'll be fine, I'm sure. Well, tonight, you guys, it's going to be a fun night. We're going to be talking about massive stars. We're also going to be talking about the fusion breakthrough at Lawrence Livermore Lab. And I actually talked to one of Livermore's nuclear scientists last night, and we talked about this process and what they had to do in order to achieve it. It's outrageous, but that and more in just a minute. I wanted to mention that this show is brought to you by, of course, Sky Tour Livestream, which is the companion stream to the Sky Tour Radio Sky Tour Radio show, and it is a amazing deep sky observatory that is live on clear nights. If it's clear tonight after the show, we may go live. Just hinting. I'm not sure. Daryl's hearing it now, so he's like, oh, okay.
Well, I looked at Weather Underground earlier. They said clear for Arizona tonight, but on windy.com, it looked like you were totally clouded over.
Yeah, the clouds that they show on windy.com are generally cumulus clouds, too, and those disappear at night if they're true cumulus clouds. So we'll see what happens.
Okay.
But Tara, of course, is always smiling at us, and I'm imagining you have some questions for us tonight as we move along. Yeah,
Sure. Sounds good. Yeah. I always have questions.
Yeah. You have questions, we have answers. Wait, somebody said that. It was like Radio Shack, right, or something. I don't know who it was. Well, anyway, so the question is like, when I tell you about Sky Tour Livestream, what is it? Well, a long, long time ago, that's how the song starts.
I remember.
Yeah. When it was just a concrete slab in the desert and on the land belonging to a nuclear scientist, the man I talked to at Livermore, he gave us the opportunity to build an observatory on his property. And we've been running it remotely ever since. And Tara, how long have we been going? I mean, how long has that building been in place?
Has it been just 2 years?
I think it has, right?
It seems like a long time, but I don't think it has been that long. So,
but don't forget, I also did it on the front lawn here at this home in Connecticut.
Add what, 4 years, 3 years to that then?
Oh, maybe another 2. So maybe for a total of 4 years. Daryl, do you remember?
Time flies, man. It's been at least 2 years.
We're having fun.
Yeah.
2-3 years.
Okay. Yeah. So, we were starting to show beautiful objects. Now the telescope to create those is right there. That's the telescope you see behind me. It's not in the building right now. It's actually being rehabbed, and it's got 2 telescopes on it. And we're going to have 2 cameras for that thing again, and we'll be able to capture beautiful objects here in Connecticut, where I live at the moment, and also continue to do it out in Arizona. And we also have another telescope coming. And this telescope is going to go in another Arizona site. That's the plan right now. So we're looking for, look at Tara's over there with a big grin on her face.
That's so exciting. It's wonderful.
It is. There's a number of locations that we're scouting right now with people that may be willing. One we know is willing. But another one may be willing to actually house a building on the property. And that's the nice thing about Arizona. People have property, and it just goes on and on and on. So what are they going to do with a little, 20-foot patch of ground over there, half a mile from their house? They don't care. And that's kind of nice, So we're going to get an opportunity to do that, and we'll see what happens. But that means, for me, what it means for me is that I have no excuse not to be streaming, because at some point, at some place in the state of Arizona or here in Connecticut, it's going to be clear. I'm not going to get a choice. I'm going to have to stream. So if I have a clear night every day of the year at one of these sites, I have to stream every night.
Darn it.
I know.
Darn it.
Yeah. I'm an astronomer. It's what I do. It's what I do. It's what I love. What's that, Daryl?
I want a raise.
Me too.
That's a lot of work, you guys. It's a lot of work.
Me too. No, everything we do is free. We do offer some things, and are going to start to offer things that will be like a subscription-based thing, like some of our best photographs that we take. We're making we're hyper processing them to make them literally big observatory quality. And Daryl actually has a story about our last image we took of the Rosette Nebula, right? You do. You said that you're using our Rosette Nebula.
Oh, yeah.
This is behind it.
For the first time in maybe 15 years, I've changed my desktop background of my computer. It's been a picture of Orion for many years, and I liked the new Rosette so much that I made it my new desktop.
So if Daryl likes it,
and that's saying something.
I guess it is. And taking it from me, if Daryl likes something, it means that it's come a long way, because he's very, very, very fastidious about the things that he will put on his desktop. At least that's what I've gathered from him. And so it can only be something good. So, as we talk about Daryl being an astronomer's astronomer, right? Kind of a thing. That's true. And we talk about Tara being a consummate artist and a brilliant philosopher. Incidentally, she sits over there with this big grin on her face all the time, and you wouldn't know, but there's a very, 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 very intelligent lady behind those glasses. Okay.
Thank you.
Probably in front of those glasses too. She probably extends her presence outward. But so the truth is that we managed to come up with quite a team. Daryl joins me in Skytar Livestream as a host, co-host. Tara is one of the people in the Skytar Livestream organization, as is Marianne Robb, who is a police officer in Arizona. So, hey, we've got all the best protection, all the best art, and all the best astronomy between us. And I think that, that's a winning combination. And one other thing, too, I have to say, and I've said this before, and if you hear it again, you're going, oh, here he goes again. There is nobody doing this. What we do is very, very unique. We create pictures that we take in the observatory. All right, let me just show you that the picture. I'm just going to take you down for a minute, Daryl, and bring you back. Same with you, Tara. Okay, and let me just move myself over here. Actually, I don't have to do this, do I? I can actually do that. I don't know. Well, look, behind me is this. Daryl's over there now. Okay, behind me is the Rosette Nebula. All right. And the Rosette Nebula is just a stunning stellar nursery. You'll see it a little bit later. And that picture was a 45-second long exposure. To get a picture like this, all right, as sharply focused as it is and beautiful as it is, would take at least 20 minutes, maybe more, 30 minutes. And you'd have to take maybe, 10, 20 sets of 30-second exposures, 30-minute exposures to get this result. But we're able to do it because the telescope we're using, we've outfitted to be 25 times faster than a normal telescope. So photographically, whereas we have a telescope that natively would be what's called photographically f8, okay, for focal ratio, it's actually f2. So f8 is slow photographically. It's like you're squinting at your object and trying to figure out some detail in it, versus if your eyes are wide open and getting more light. Okay, our eyes are so wide open that we get all this light in and can see things just amazingly. And that's what the f2 system does. So we get things in a factor of 25 times faster than the previous version of the same telescope. And in general, that much times faster than most telescopes out there. So we really make a good stab here at the universe, and we will show you, because we can do that so fast. We go from object to object to object. You know, we have chats. You know, people from all over the world come in and they chat with us. They listen. They ask questions, and sometimes they'll say, "Hey, can we see this object?" And Daryl will chime in and say, "Yeah, that one's up already. We can go there. All right, cool. Let's go there." And so we'll steer the scope. Now, it's really interesting to think about, but the telescope is fully remote. And the telescope itself is in a building that we made completely green. Now, I don't mean the color. I mean, energy-wise, it uses all renewable energy. It's solar power, which provides energy to batteries, courtesy of the landowner. And the rest of the systems in there, I built remote observatory software, wrote the programs to actually control certain things, the housekeeping stuff, moving the roof on and off and turning on and off the telescope, etc. And then we use other commercially available products to actually control the telescope. And we're doing it from 2,500 miles away. You know, so it could be rainy and nasty here, and sometimes it is. And out there, it's a pristine, beautiful night. So I guess in a way, it's just my way of saying I have to see stars tonight. And they're usually very pretty stars. And so that's why we do it the way we do. But anyway, so that's Sky Tour live stream. If you want to know anything about us, if you're really interested in more about us, you can actually check this out here. Go to skytourlive.org, right there along the bottom, or skytourlive.com. We have both. And skytourlive.com is the portal that brings you to the live stream online, where you can go check out the observatory. It also has a link. The most important thing now, when we take these pictures, is that where it ends? No, not at all. When we take those pictures, as we're taking the final picture, when that last picture gets taken of a certain object, it is shipped out of the observatory and brought up to a server that we've created. And this server makes these images available to you literally within 30 seconds of us taking the picture. Full resolution. Okay? So way bigger than your screens on your desktop. And so you get a lot of imagery this way. And it's all available pre-processed as well as the raw. So you get everything. So that's it, you know. And I think Daryl, he's had a good time looking at some of the composites we've created, where we go move over a field and down and over, and we take images of the whole big region. Right?
Mosaics, sure.
Mm-hmm.
I have some ideas. I'd like to talk with you about that.
See that? Course. Yes. Well, fine. That's good. And then, of course, Tara, being the artist, I mean, she can really appreciate some of the stuff we do that just looks so stunning.
It's very humbling, these images.
Oh, they're beautiful.
They're just incredible.
Yeah. Isabella Melamed is a great help as well.
Oh, yes, Isabella Melamed. See, that's the thing. We have a great community. The people that we have that join us on each of these Sky Tours, Isabella is from Sofia, Bulgaria. And she does all of our tables of contents for all the videos. So when you go to the video on our Sky Tour live stream with Mark D'Antonio YouTube channel, you can actually click on the different chapters now, because the table of contents exists for each. So if you want to know what we looked at, you just look at the description. Oh, there's the Iris Nebula. Okay. And, you know, then you go there and you just literally have to do a couple of clicks, right? And you'll see this. Oh, look, there's the Iris Nebula. All right.
Wow.
Yeah. You know, and then you can see this dust that's just hanging out in interstellar space, just waiting to make stars and planets. So there's so many cool things out there that we're doing, and that we have available. And thanks to Isabella and Daryl and Tara and Marianne, we bring this to you live and for no charge. It's a free education in astronomy too, because we don't just show you the objects. We tell you the nature of the objects. We tell you what they mean. We tell you where they come from. Like when I showed you that picture just now, I talked about stars and planets forming there. Well, we get into a lot more detail when we actually do the stream, you know. So it's pretty cool. You know, so hopefully, if you haven't joined us at Sky Tour live stream on YouTube, find us again at our location. Our location, as we said, is right here down below, skytourlive.com or skytourlive.org. And from there, you can go into the live stream channel and just join right there. Click the bell, get notified.
Subscribe. Yep.
Subscribe. Yep. And we're just surpassed 7,500 subscribers. A small amount for a YouTube channel, but it's climbing. It's climbing. You know, we actually had a celebrity come in the other night. What was that 2 nights ago? We had one of the hosts from Coast to Coast AM came in.
Good.
Yes, that was Connie Willis.
Oh, okay, yeah.
Yeah, and she came in for an hour and hung out with us and talked to us, and she brought a whole slew of people with her. And it's like, hey, you know, so we got to, you know, hear from them in the chat, and you know, we're very, very responsive. If you write something in the chat, if we don't see it, that's the only reason we won't respond to it, because we're always looking at the chat. Now, when I'm in there, I'm doing 5 things at once. I've got 2 monitors, and they're both filled with stuff. You know, I've got one thing here, and I got 2 eyes, so I figure I can just split my vision, you know, and look at them alternately. But if we don't see it, it's because if we don't respond, it's because we just didn't see it. So sometimes we have to put the chat on a delay so that it doesn't go away on us too quickly, because I would hate to miss a really good question from someone. And there's no planned questions, no planned targets. Many times we just go to the different targets that match the things we're talking about, you know? So it's like a pretty cool thing. Anyway, so what are we going to do tonight besides just go on and on and on about an observatory you can't see right now because we're not running it, okay? It'll come online at 8 p.m. tonight Eastern Time. And if it's clear, we'll go online too.
8
but
p.m., that's my dinner time.
That's right, it's dinner time.
6 o'clock my time.
Yeah. 8 p.m. Eastern Time, yeah. That's when the observatory opens up out in the desert. I have it timed so that the power comes on to the building at 8 p.m. You know, with the winter, I could actually have that going way longer. I could have it start at 6 p.m. desert time, you know, mountain time, and so forth. But I it's okay like it is, because I'd also be tempted to be in there all the time, and that's probably still not good either. You know? So one of the things that I wanted to mention to you tonight, with all the things going on, certainly some of you, many of you maybe, have heard about the breakthrough at Lawrence Livermore Lab. Now, the nuclear scientist I talked to has his name on many of those things that you heard about, okay? He was part of these programs way back in the beginning when they were first starting and carrying through to fruition in some cases. So I talked to him about the fusion discovery and the fusion operations. The significance was that he talked about this, because this is one of his things he did was, if you saw in the newscast, they were trying to fuse a small deuterium and tritium pellet into an isotope of helium. That doesn't sound like a whole lot of anything, right? But, okay, let's talk about what this is. Okay, deuterium and tritium are isotopes of hydrogen. What's that mean? It means if you add 1 neutron to a hydrogen atom, it becomes deuterium. Add 2 neutrons to that same hydrogen atom, and so with a total of 2 neutrons in the nucleus with that proton, that's tritium. Now, tritium and deuterium are nuclear fusion fuels. Tritium is the nicest radiation you can have, okay, because you could rub the powder on your skin, okay, and it won't even penetrate your skin. You could inhale it. Oh no, I've got tritium, radioactive tritium in my lungs. Am I going to die? No, drink a lot of water and go to the bathroom a lot, and it will leave your system. It's not cumulative radiation. So you can flush it from your body. And so that means that tritium and the fusion potential for the use of tritium makes this process so much safer than fission. And I'm going to talk about fusion versus fission too, because I think it's important to understand the difference. Now, we can do that now, I guess. When you have a fission system like we have now, all right, the nuclear reactor is basically a fancy way to boil water. Daryl and I were talking earlier, and he said, "Oh, it just boils water to turn turbines." Well, that's exactly what it is. But how do they do it? Well, they make use of natural elements in our crust that have been refined, and isotopes made up. Different types of the same element have been made in what are called breeder reactors to actually make these very refined fuel pellets that go in a strand, ding, 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 in like a tube. Okay, click, 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 fill it all up. Now you put another one next to it, and another strand of material over here, another strand of these pellets, and they're going to interact with each other. They're going to send off particles that interact with the others and heat them up. Now, left unchecked, those particles will heat them up so much that these strands in these metal tubes will just melt. Okay? So what they do is they immerse them in liquid, right? Sometimes water, sometimes actually lithium. Okay? But if they stick them in water, it heats up the water. The water is sent through a heat exchanger system where the heat is transferred to another batch of clean water that's not been in the radioactive reactor. And that hot water is used to drive turbines and so forth and make power. That is just a so totally simplified version. But what happens with this fission project is that if you have these in there and you want to moderate that reaction, you don't want that reaction to just keep going. What you do is you take graphite rods and you lower them down between your two stalks of pellets and tubes. And those graphite rods will absorb the particles coming off of these guys and of these guys and not allow them to reach each other. So to shut down a reactor, you just put those graphite rods in. That's called a scram. Okay? It's like a reactor, immediate reactor shutdown. Well, if you pull them in and out at various levels, you could put them down in 6 inches and get half the reaction. Put them in 3/4 of the way and you get a quarter of the reaction. Okay? Move them in a quarter, you get 3/4 of the reaction. So you can moderate how much of that reaction occurs. But to move those rods takes energy. You have to use electricity to lower these rods in and pull these rods out. Okay? So in other words, fission is like operating inside a deep valley where the only way to get the reactor up here and shut off is to input energy to move those graphite rods down in there to get the reactor out of this deep well of full power operation. So you have to add energy to get out of there. Okay. Now, fission, on the other hand, is a different process. In fission, you're not depending on these elements in tubes that are interacting with each other. You're making an interaction occur by bombarding a pellet with special lasers all aligned and accurate to within a trillionth of the same energy output as each other. Okay. And it's like it's a reaction teetering on the brink of a very, very pointy hill. So it's always doing this. Okay. And if you miss one thing, that reaction is going to fall off. And what happens? Does the building blow up? No. Does it melt down? No. It shuts off.
You said fission. You mean fusion?
Fusion is up here. Yes. Sorry.
Yeah.
So
while
fission
you're
is down
talking
here. Fusion is up there.
Yeah. Charles Smarr has a question. Does fusion create any secondary radiation in the reactor? Neutron bombardment? Question mark.
Well, yeah. I mean, there are output. There's output from the fusion reaction, but they are not radioactive particles that can hurt us. Okay, they're contained within the reactor, and if they got loose, they wouldn't be something that would destroy the environment. All right. So for fusion, it's much safer. Fission is the bad guy, right? Fukushima, that poisoned 5,000 square miles, I think, of Japanese territory. Chernobyl, the town of Pripyat was just completely eliminated as a zone you could live in. And 3 Mile Island had a steam leakage into the atmosphere, which sent radioactive material up into the atmosphere. Fission reactors. Fission, right? And that was causing, what were you going to say?
Nothing.
Oh, so the fission reactors were actually interacting with each other, and they couldn't adequately shut off the reaction. In Chernobyl's case, it was actually almost like a mislabeling of a button, which or a misunderstanding of the labeling on a button, which caused the whole Chernobyl explosion. Okay, the reactor basically popped its top. It was a graphite caps on the cover of the reactor. 3 Mile Island was a overheating situation where they had to vent to the atmosphere in order to preserve the reactor. Fukushima was an inundation by a tsunami, which shut down diesel generators designed to be able to put those rods in that I told you about. So without those diesel generators, when you couldn't have anything else going, those rods couldn't be operated. And therefore, the reactor pools boiled till they were empty, and they melted down and caused explosions of steam. Hydrogen built up in the buildings, blew the building to pieces. And it was so powerful, you could see the shock wave leaving the building. Now, the buildings were designed to blow up, blow out like this as a safety precaution. Go figure. But that's true. And so the Fukushima explosion, they found elements of fuel pellets miles away from the reactor. They had been blown out. So obviously fission is not a good thing. Okay. Yes, it provided energy, but at what cost? At the cost of poisoning, So going back to the fusion, all right, what is fusion? Fusion is taking, hydrogen, an atom of hydrogen, and colliding it with another atom of hydrogen and compressing it together. And once you compress it together, you actually make an element that has 2 protons in it, and there's some neutrons in there too. Okay, a couple of neutrons. All right, and you've made helium. So that's it. It's like in stars. Hydrogen is made into helium, which we're going to talk about later when we talk about high mass stars. But in the case of fusion, the process to make that happen is extremely complicated, and like I said, in the case that they used this last time, they used 192 lasers, all pointing at something the size of a BB, a little round BB. And that little round BB was a deuterium tritium pellet that we talked about, and it was inside a chamber, and these lasers hit it. Now, they were able to, in the past, hit a pellet like that and create a single reaction, a single event where these pellets would be converted to get some helium out of them. Okay, so they could make helium work. They could make the fusion occur. The problem was you didn't ever have a sustained reaction where you start to basically light the match and it goes off on its own. You just sit there and watch. Okay, they couldn't do that before until now. Okay, now they were able to light the match, so to speak, and the reaction progressed until they turned the lasers off. Wow. Remember, fusion's like on a teetering hill. Anything goes wrong, the reaction shuts down. You shut off one of the lasers, out of 192, just one, the whole reaction shuts down. Okay? So technically speaking, they were able to get more energy out than they put in with all these lasers. That's the technical result, which is why it's very significant. We've been trying to reach what's called a break-even point, where you get back at least as much energy as you put in. But this got back a little more. Now, there's some controversy. Daryl had mentioned some earlier tonight, and we were talking about whether it was really, truly a net energy gain. But from the Lawrence Livermore proceedings, it was an energy gain. And this paves the way for a massive number of technologies. Now, first of all, I actually have a vision for a glass or soda can size fusion reactor powering, people's houses or clusters of houses down the line. There's no reason that can't be. Remember Doc Brown? Hey, Marty, you got some banana peels? Throw some garbage in Mr. Fusion. Mr. Fusion on the back of the car. Remember that? That was so cool. Yeah. Mr. Fusion was awesome. Well, the bottom line is that that, of course, is a long way away. But the commercialization of fusion will occur, and we will be able to have fusion energy someday.
It's
And
only 20 years away.
it's only right there. We talked about that too. It's only 20
always
years
only
away.
20 years away.
Yeah, I heard 10 years,
I
but
heard 30.
hmm it's only 20 years away. Only 20 years away. Yeah. Well, now it's only last week that we got energy out, plus net energy out of it. So we're looking at it happening probably for real in the next 10 years, 15 years. We might see a more refined process where we'll hear about a Lawrence Livermore fusion reactor that's been running continuously for 100 days and fusing. That's what I'm guessing. But again, it's on that tiny precipice, really balanced finely. If you change one thing, it shuts off. Okay. So that's what's interesting about the fusion reactor versus fission. Fission, you can get a meltdown because you can't put those rods in. You can never get out of that valley, that valley of energy you need to actually stop the reaction. But fusion is the exact opposite. Makes it so much safer. And the products you can rub on your skin. Maybe to become a beauty aid. Oh, look. I rubbed some tritium on my skin. It got rid of all my outer layers very nicely. Right?
You have the tritium woman knocking on your door.
Oh, that's
Yes.
right. The tritium
Yes.
salesman.
Yes.
Ding
Hi,
dong,
I'm from 1-800-GO for tritium.
Tritium calling.
Yeah, I am. Remember Avon calling? Tritium calling. Good one, Daryl. Yeah, so
Still in all, though, I mean, it's not like you don't want to drink heavy water.
no, but you can, and that's the thing. You can drink heavy water is water where the hydrogen atoms have an extra neutron in them. Okay, like deuterium, and then you have it mixed with oxygen, so you get that's why they call it heavy water, because you have an additional neutron in the nucleus of the hydrogen atoms. But believe it or not, it's not radioactive, and you can drink it, but it has a cumulative effect if you drink a lot of it, and it can damage tissues and stuff, but not through radiation, but just because of the nature of how the body processes water. And so if you can drink a small amount. I did find that out. And you know what? I probably would, just to try it out. And actually, I heard that it doesn't taste any different from regular water. Wait a minute. Oh, this is the heavy water. Sorry, yeah. It feels heavier.
Yes. It's the glass, Mark.
Oh, she's right.
Plus, it's not
Yeah.
cheap.
Yeah, I'm sure. Yeah, can you imagine how much that amount of heavy water would cost? That's quite a bit. Yeah, but it doesn't taste any different from regular water. You wouldn't even know you're drinking it, but it can wreak havoc on your system because biologically we're not tuned to manage the consumption of heavy water. So, but there's another ramification to the discovery of a net fusion reaction and a potential fusion reactor. Now the question is, what kind of particles could we generate with a fusion reactor? Well, we have talked about, I've actually lectured about this around the country, actually, and it has to do with ways in which we can utilize fusion in order to travel through interstellar space. Now, you hear about science fiction and fusion reactors. It's the XB952 fusion reactor is going to power our trip to Jupiter. So you hear about that in science fiction, but what does that mean? It means something that we can utilize as an ongoing source of energy. But what's the nature of the energy? The nature of the energy is particles that you generate that allow you to do something that will move your ship from one place to another, right? And that's what that's all about. And so when we talk about it and we talk about fusion, and by the way, this was the Livermore, one of the fusion chambers at Livermore. The actual chamber that was used was back when the scientist that I was telling you about was doing the fusion research. It was literally 4 stories tall, and the tokamak, which is a previous iteration of what the chamber they used, you could fit 50 of those inside the same building, and the tokamak was the size of a house. So you're talking about 50 of them. So the building was pretty big. I think he said 40 stories actually in size. overall volume. So it's actually a very, very big space, very big thing, where this is just a small little area, but it's a pretty picture from Livermore. So that's the only reason we put it up. But the thing about the thing about this, let me just get rid of this. We need this right now. The thing about fusion and what we could use and what we could do with fusion is it takes us, like I said, outside the planet Earth. It takes us elsewhere. Now, what would we use to do that? What's the concept? To understand the concept, we have to go and take a look at the 4 fundamental forces. This is something we've talked about in the past. All right. In the upper left there, you have the strong force. In the upper right, you have the weak force. In the lower left, you have electromagnetism. And in the lower right, you have gravity. Now, let's start with the strong force, okay? The strong force is what's inside of an atom. It's actually what controls whether a proton with another proton next to it can stick together. It's like Velcro. Think of it like Velcro. The protons are kind of stuck to each other like Velcro. Now, the strong force is actually only as powerful as about the size of a proton. So you have to have these protons really close to each other for them to actually stick to each other effectively. And so, but the strong force is the strongest force in the entire universe. And the reason is because 2 positively charged protons together would have a force of 20 pounds on these tiny little particles, pushing them away. And so that force has to be overcome by a very, very much more powerful force. That repelling force is overcome by the strong force. And the strong force can hold various protons together all the way up to about 118 of them. Okay. And then beyond that, the field falls down and falls apart a little bit, and you're not really able to get any atoms of much higher than 118 or so, which is why our periodic table right now stops at 118. But we'll probably find more. We'll probably be able to generate more. But anyway, so that strong force is what holds atoms together and protons together, nucleus especially, because they're all positively charged particles in there. And in order for a proton to be slammed together in the first place, you actually have to do it at high temperature and high speed. In other words, high kinetic energy, the energy of movement. And the reason is because they have to overcome a force called the Coulomb force. And that's the force that would prevent protons from getting anywhere near each other. All right. But if you get past that Coulomb, it's called the Coulomb barrier. If it's past that barrier, then they'll stick to each other. And to do that, you need them moving at high speed. The protons have to be moving at high speed. That's why we build accelerators that move protons very, very fast. So we can collide them and they can hit each other rather than just go around each other effectively. So this Coulomb barrier is what we're overcoming by accelerating particles very, very high speed. And a fusion reactor could do that, right? And we would be generating particles from these collisions, right? And see new particles potentially that we've never seen before. Now, going back to this diagram, the weak force up at the top right, that has to do with something called beta decay. And there's beta decay plus and there's beta decay minus. The minus is the reason you're here, right? And the plus is the reason that there is a shift back and forth in the periodic table sometimes of elements. For instance, you could, for instance, take a hydrogen atom and make it into a helium atom, all right? You don't have to collide the hydrogen atoms together. The hydrogen atom just has to allow a neutron to come in. Now, that Coulomb barrier would prevent another proton from coming in unless it's high speed, but neutrons don't feel that. They don't have the barrier because it only affects charged particles, right? So the neutron has no charge. So it could go right into the nucleus, and there's a process by which a neutron can be converted into a proton. Now you have a one neutron nucleus, or one proton nucleus with one neutron, and then suddenly you can have a 2 proton nucleus with no neutron. Well, 1 proton nucleus is hydrogen. A 2 proton nucleus is helium. And now you've gone up the periodic table by 1 element. Yay. So that process of beta minus decay will cause us to have new elements down the table. And that happens in stars. They do this thing. It's actually called neutron capture. They actually capture neutrons, and then they get converted to protons. And so we actually see how stars do this process. Here's a chart, that famous periodic table. If you look at the green things everywhere, that says dying low mass stars. We've been taught that stars make up to about iron, number 26, in their cores. Well, how come a star like the sun then can make niobium, okay, zirconium, yttrium? How can it strontium? How can, the number 38, 39, 40, and 41, okay, the greens? How can our sun do that? Well, it's because our sun is doing exactly what we just talked about. It's capturing in the nucleus of another atom, it's capturing a neutron, and that neutron's converted to a proton, and that makes it one more in the table. So as the star dies, our sun will do this, I should say, when it starts to die. As the star dies, it's going to start creating these elements. And because it takes 1 billion years or more for a star to actually physically finish itself off, it's going to be able to do this process for a long time and generate lots and lots and lots and lots of particles and other elements that are farther down that periodic table. And we populate the periodic table this way, Now, so that's the weak force. Electromagnetic force, well, that's just magnetic fields and light. And of course, that's very important too, naturally. That's the lower left one. All right. But I really want to talk about the one in the lower right. Gravity. Gravity is an oddball. See, for the other ones, strong, weak, and electromagnetic, we can describe the particles, as waves or as particles. Okay. For gravity, we could describe it as a wave now. From before, where we just knew how to calculate its intensity, now we can describe it as a wave. And that is something Daryl mentioned in one of the other radio shows. You remember the LIGO detectors, Daryl, that we talked about? Right?
Sure.
The laser interferometric gravitational wave observatories, LIGO.
And the Virgo in Italy.
That's correct. Absolutely right. Yeah. And these were able to detect gravitational waves from the merging of neutron stars or black hole mergers. They generated such a disturbance in the force, okay, that they actually created gravitational waves, something that Einstein predicted we'd never see, but we did, okay? And these gravitational waves propagated throughout the universe, and we saw them. But because the Earth is so big, essentially, the wave struck one detector before it hit another and allowed us to triangulate and figure out the intensity, where it was coming from. And we're able to figure out that these came from billions of light years away in particular case. So these gravitational waves then taught us something. Wow, gravity can take a wave form. And gravity might also be able to take a particle form. Now, in science fiction, we've heard of gravitons, right? Oh, what are gravitons? Gravitons are the theoretical particle that we don't know yet, we don't find, we haven't seen, that holds you down into the chair you're sitting in, or the car you're driving in, okay, or the bed you're lying on, okay? Wherever you are, gravitons are doing their work. They're holding you down effectively, or depending on your perspective, pushing you down, okay? And so the graviton then is something that is elusive, and we want to find it. Well, there is a theoretical particle that once we find Earth gravitons, there's another type of graviton that might be out there. And it's not just Mark D'Antonio saying this as an astronomer. It's physicists, aeronautical engineers. Okay. My friend Bob Schroeder writes about it in the book, The UFO Enigma, Solving the UFO Enigma. If you can get a copy of that book, more power to you. It's a great book. I have one behind me somewhere. But the bottom line is that if you look at what Earth gravitons are relative to this other particle that a fusion reactor can generate, these other particles are called Kaluza-Klein particles. And Kaluza-Klein particles are also gravitons that are 10 to the 16th times more powerful than our gravitons. Now, if you have a ship, okay, and this chapstick will serve as my ship, is the SS Chapstick, Okay. And you surrounded your ship with these Kaluza-Klein gravitons. Okay. Several things would happen. Number one, the ship would look like it's shimmering to you, and you might lose sight of it. It might blink out. It might look like it's changing. It might look like it's warping. Okay. And why is that? Because the Kaluza-Klein graviton also generates micro black holes at the same time. And if you surround your ship with these Kaluza-Klein gravitons, then your ship will seemingly vanish from your eyesight in a way that doesn't make any sense because we've never seen it before. Now, this is something related to string theory, and the property of this vanishing, it has to do with these micro black holes, because the micro black holes are surrounding the ship along with the Kaluza-Klein gravitons that are actually these micro black holes are absorbing light that's hitting them.
Sounds like a cloaking device.
Doesn't it, though? Yeah. But in addition, the micro black holes are absorbing a tiny bit of the atmosphere, but they're also doing something else. They're absorbing the gravitons of the Earth trying to get to the craft. So they prevent gravity from reaching the craft. So the craft would effectively just float. And there's so many reports of UFOs just floating like leaves on the wind. And this could be why. I won't say it is why, because who knows? We don't know yet. But it could be why. Now, the shimmering, the vanishing, the color changes, all that stuff is also something that could be and would definitely be evidence of the usage of these Kaluza-Klein or KK gravitons. Now think about that. We are just looking for these types of things now. We're actually, we collectively are building another accelerator near CERN that's specifically in part looking for KK particles. We wouldn't be doing that if we didn't think they were there and if we didn't think that they would, be important to study. This is important news. So coupled with the fusion thing, which I'll get to in a second, we also have this thing about the KK gravitons now that they're possibly going to be investigating. Now, why is the graviton so important? Why the KK thing? What's the big deal? Well, the big deal is this. We live in 4 dimensions, X, Y, Z moving through time. Okay, everything we know, okay, this water, everything we know is moving through the 4 dimensions of our universe. And so if we could generate, using a fusion reactor, we can generate these Kaluza-Klein or KK gravitons around our ship. Those don't exist in our 4-dimensional space. They exist in a 5th dimension. Think of it as a little doorway between our space and another region over here. This region has a name in this particular string theory variation, and it's called the bulk, B-U-L-K, like bulk produce, bulk count, bulk stuff. And on this side is where we live, and we call it our home membrane. They like to fool you with names, but this is our XYZ moving through time over here. Okay, over here, right? This is our bulk. Now, the bulk is a highly warped space. You generate these Kaluza-Klein gravitons, they go around your ship, and it draws your ship to where they live, which is in the bulk. That's where they come from. And so when you get there, here's the consequence of going into the bulk. Everything around you is closer. The distances are all exponentially closer to you than when you're out here in the 4 dimensions. So the farther in you go, the more particles you generate around your ship, the farther in you'll go, the more warped space becomes, and the smaller distances become. You got that? It means, go ahead, Tara.
It's the folding of the burrito.
Effectively, right. That's right. Okay. It changes the distances. So, for instance, Alpha Centauri's distance is 4 light years, right? Just over. If we wanted to get there with the fastest technology we had today, okay, the New Horizons spacecraft, right, which a human being couldn't be in, all right, but if we wanted to, it would take us between 10 and 11,000 years to get to Alpha Centauri. So not very economical. We get horrible gas mileage, right? Well, using this process, and if we could actually go into the bulk with our spacecraft, use the bulk to actually go and go out. Actually, go here. Here's where I had the bulk. Go into the bulk and get that distance to Alpha Centauri shortened enough. We could then punch back into Alpha Centauri and be there in a very short amount of time. How short? One calculation puts it at about 20 minutes. Weird as that sounds, it's not weird when you look at the possibilities and when you look at the actual work that's been done. This is not fringe science by guys who make YouTube videos, okay? Guys that sound authoritative and make it sound like they know what they're talking about. This is aeronautical engineers and physicists talking, all right? And the rest of the physics world isn't saying it's ridiculous. They're not saying it's crazy stuff. They're saying, well, we're not investigating that right now. We're doing other things. They're not saying it's wrong. They're just not devoting the time required to understand it. Not yet. Not a lot of them, but many of them are, and they actually are on the side that says, well, someday we can do it. Why am I talking about this? Because I'm crazy. No, because with the breakthrough in this net positive fusion that we've achieved at Lawrence Livermore, it means that the likelihood of a fusion reactor is much closer than it was 3 weeks ago. Okay. And yes, it still may be 10, 20 years away, but a very real 10 or 20 years and not the 20 years later, we're still waiting kind of a thing. So if that's the case, it means that we can generate these particles. We could make a chapstick and surround it with these particles and see what happens to it. If it starts to shimmer and pop and look like it's vanishing, like mine just did, then it would be a definitive step in the right direction to understand that maybe we're on the right track. So the future is very, very bright with fusion for a lot of reasons. So
I think you'll see. It's like we talked that. Well, for all that fusion can do for us, just like nuclear fission now, ultimately all we do is boil water with it.
yeah, to make a
And
reactor.
if we
Yeah.
ever came up with a fusion drive, so to speak, we'd just be using it like a campfire to heat the fuel and spew it out the back of the engine at a much higher velocity than we can achieve with present chemical rocketry.
Right. And that's another thing too. The fusion rocket concepts are replete across NASA design work and everything. That you see fusion rockets.
I
They are much better than fission rockets, which also exist.
Oh yeah.
In fact, there's a famous UFO case, Daryl. I don't know if you know this one. The Cash Lundrum case. You familiar with that one, Tara?
It sounds familiar, but I don't know
Yeah.
why.
These people were driving along and they saw this object spewing flames in the air, and it was being followed by helicopters. Well, somehow they got close to this object, and they ended up with radiation burns and hair loss and everything. Well, that premise was that there was this extraterrestrial device in trouble, and I personally don't think that an extraterrestrial craft would show up with a fission reactor. Okay, that's just not going to work. So most likely it was a black project, and unfortunately it became a white project when these people saw it. Okay, it became public, and they got a heavy dose of radiation. I think it was Betty Cash. I think she died of lung cancer. I'm not sure how old Lundrum was when she died, but the bottom line is that this case was very famous, and it looks like it was a case where there was a nuclear-powered craft being tested, and the nuclear-powered craft actually ended up poisoning them. And of course, go ahead.
There was a nuclear missile the U.S. was supposedly working on that it could fly for weeks or months on end, and it spewed dangerous radiation the entire time.
Yeah, I
They
think
could
it was.
they could send it up, and it had an extreme loiter time, and they could drive it around until they saw a likely target. And in the meantime, it just spewed radiation all over the place.
Wow.
Yeah, what will we think of next? You know, so I think that we're going to be coming up on a break here in another
We
couple
have
of
2
minutes.
minutes, it looks like. Yeah.
So we're going to set up what's coming next. We're going to actually have Daryl's going to run us through a wonderful deep dive.
Yay.
And what will you tell us about, Daryl? What are we going to talk about?
Oh, I'm going to talk about the change of the seasons and, as
Okay.
usual, what's up in the sky tonight and how we're moving into winter and what constellations are up and stars are up and
Cool.
objects are up and let you show some objects to them and
Cool.
Okay.
that's about it.
All right. And as a little teaser, Tara's got some questions for us as well.
I have a question for you now.
Okay. We've got a minute.
Yeah, real quick. Are there dangers going into the bulk? I mean, do we know what is in there? Is it just the rest of space? I mean, it's kind of scary. So
it's another dimension. And the thing is, here's the problem. If we don't continue to generate those particles around the ship, they also protect the ship. That's kind of important. So if they stop protecting it, that ship's going to go, and that's it. Your trip is over. So clearly, a species that is, that's when your fusion reactor, you don't want that to fail. You want backups, okay? But technically, you're only in it for a very short amount of time, okay? I mean, everything's a finite time when you're doing this kind of thing. But maybe you're in it for, say, 6 seconds versus being here for like 2 minutes or whatever. But the benefit is if you go back and forth, oscillate between the two, you could be here and not here. Whoa, that's cool. Yeah. But we'll talk about more of this stuff when we get back from the break. What says you? This should be fun. All right. We'll be right back. This is Skyter Radio, and we'll come back with a lot more.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
Are you looking to go on a faraway journey that is magical and mysterious, reaping on mystical legends? If so, then Mysterious Adventure Tours is perfect for you. Imagine a voyage to explore ancient mysteries of Ireland, haunted majesties of Scotland, or their chilling Birth of the Vampires in Romania. These small esoteric getaways are limited and do fill fast. So, go to mysteriousAdventuretours.com and book your trip soon.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Hey, welcome back to Skyter Radio. I think I'm Mark D'Antonio, but I'll just have to check my probability counter to see if that's changed. I mean, you know, we've all seen Hitchhiker's Guide to the Galaxy and, you know, the improbability drive that powered the ships. Glad that's not us, because I could just suddenly turn into like an iron or something, or a bowling ball just sitting here, you know. Right, Tara? I mean, I don't know.
Sorry, it was on mute. Yeah, that's funny.
Daryl, I would love it if you could take us through the sky tonight. This is Deep Dive with Daryl, ladies and gentlemen. Take it away, Mr. Mason.
Okay, I hope this works.
Just talk nice and loud.
Yeah, real loud.
Whoops, give me just a second. It looks like Stellarium's controls are changed. I don't see it. Darn it. Bear with me here.
We're bearing.
Bearing.
Well, while he's looking for it, I'll just tell you a little later when we'll have Tara ask some questions, and we want to get into what happens with massive stars that are 4 to 8 times the mass of the sun. This is where we get fireworks. Okay, when these massive stars run out of their energy, their fuel, it becomes a fireworks display like none other. And we've witnessed some of this before, but we'll come back to that in just a minute because it looks like we've got a stellarium up. Daryl?
Yeah, okay. I'm afraid I'm not going to be able to show the analemma, the skinny figure 8 that you see drawn out in the middle of the Pacific Ocean on globes and maps. I'll consider myself lucky that I got this. Okay, as usual, I'm going to start over in the west, right at sunset. I have the atmosphere turned off, so the sky is dark, but you can still see the sun there. And we'll go just a few minutes more and make the sunset now. We are really close to the winter solstice, so the sun is setting really early. The earliest sunset actually happened back on December 7th. Earliest sunset, latest sunrise do not happen on the solstice. They have a few weeks, they rise and set a few weeks on either side of the solstice, but the solstice is the day with the shortest length of sunlight. So the sun just set, and right now Venus and Mercury are both up over in the southwestern sky. You probably won't see them unless you have a dead flat horizon after the sun sets. If you get out there with binoculars or optical aid, you may just be able to pick them out. Now, Venus is rising and is going to continue rising up along the plane of the ecliptic for months to come. Mercury orbiting the sun so fast, well, Mercury is about to start dropping again and move back into the morning sky. Venus is going to continue rising up for months on end here. And you'll see Saturn is up in the west-southwest right now, and then Jupiter is up in the south. And I'm going to start rolling things here. From west to south at the same time. Okay, the sun just set, Venus, Mercury. Here is Saturn. As the night progresses, you'll see Saturn is setting by 9 o'clock at night now, even before 9 o'clock.
That's right, huh?
Saturn is gone already.
Jeez.
And Jupiter is going to set by midnight. And so there goes Jupiter. And you see it's almost midnight. Jupiter's about to set already. The nice thing is, the stars of fall, Cetus is going away, Aries, Andromeda, all those, Great Score of Pegasus, they're all setting in the west now. But hey, look, the stars of winter are at prime time now. You can see the winter circle, Aldebaran, Capella, Castor, Pollux, Procyon, Sirius, and Rigel. And right now, we're at about close to midnight here, Orion is already transiting the meridian, that green line that runs from north to south, passing straight overhead through the zenith. Orion is already transiting the meridian by midnight, and it's moving from the morning to the evening sky. It is becoming an evening object. That is, it will already be up at sunset, and it will set before sunrise. But right behind it, here comes Sirius, and watch this. I'm going to change the days now. We get to January the 1st, and I'm going to set it to midnight. So this is December 31st at midnight. Okay, bang.
Happy New Year.
We'll go on. Happy New Year. Sirius transits the meridian right at midnight. And it's just sort of a cosmic coincidence. It doesn't really mean anything, but it seems to represent a lot, to me at least, that the brightest star in the sky transits the meridian at midnight, and it also has moved into the evening sky now. That's just something to watch for. I go out every New Year's Eve at midnight when we switch to, 2023 will happen this year. They shoot fireworks off the top of Pikes Peak, the big mountain just west of town here. And it's an annual event. It's always something to watch for. But not only do we get fireworks off the top of Pikes Peak, but there is Sirius doing his thing. It's a famous twinkler of a star that flashes pretty colors. And that is the other fireworks happening at midnight on New Year's Eve. And just as an aside, also this time of year, we are closest to the sun on January the 3rd. The Earth is at perihelion, that is, Earth is closest to the sun, and that's happening also soon after the winter solstice, and it's just another, you can take as another sign that we are entering a new year, that we're going to start another lap around that skinny figure 8. Aside from that, I'm going to go back to, let's see here. We're the 18th. And in recent streams, we have to wait for Orion and his friends to get high enough to see over the roof of the observatory to the east. But we are now able to check out Orion and Monoceros. The Rosette Nebula that Mark showed earlier is right there, that little pink spot you can see. Here, I'll do this and make it even, whoops, that didn't work. But now it's time that we can catch Orion at a decent hour. We can see all the great objects of the winter time. We have the Crab Nebula right here next to the tip of Zeta Tauri, one of the horns of the bull. You might remember that Mars was in opposition back on December 7th, and that was the night that the moon occulted Mars. We got to see that. That was really cool. I got to see both the disappearance of Mars and the reappearance of Mars. I had my little telescope set up out in the front yard, and I ran outside and got to see both of them. It was fighting weather a little bit, but it cleared later, and actually got a really great view of it. And Mars was only about 17 arc seconds across, while the moon was half a degree across. Half a degree is 1,800 arc seconds, and Mars being 17 arc seconds, it was about 100th the size of the moon in the sky, but I could still see detail on the face of the planet. Could see the North Polar Hood, could see Martian terrain called Cimmeria. It was really cool. And the other thing to note here is a few months ago, Mars was all the way here outside the horns of the bull, just past them, toward Gemini. And as we passed Mars in opposition, Mars went retrograde and started moving west to east, east to west, backwards across the sky, until now Mars is all the way back here, back toward the high 80s, the head of the bull right there. And in a few months, a couple of months, Mars is going to start moving in direct motion again, west to east across the sky. But we actually got to see Mars move this way. When I first saw Mars back in September, Mars was right here. It was like the bull had two red eyes instead of one, Aldebaran being the other.
That's right.
But then Mars moved this way, and then as we passed Mars, Mars fell back. And give it a while, and Mars is going to start moving this way again toward Gemini. And it'll be moving in direct motion for for the next 26 months until the next opposition happens in 2025, I guess. But anyway, back to looking on our live streams. We have got to see stuff in Perseus. We were still spending time in, whoops, I shouldn't have done that. We were in Cepheus. We were in Perseus. I'm all Perseus here.
Cassiopeia.
Auriga, Cassiopeia.
Yeah.
Cassiopeia.
Andromeda Galaxy still.
Uh-huh.
Yeah.
But
Triangulum Galaxy.
Yep. Let me get back here. But here we are now, and by 10 o'clock at night, we can see Orion. And we give it a few more weeks, and we'll be able to see Sirius and all the cool stuff down there. Messier 41, and getting into Puppis down here, and Messier 46, all those cool things. And again, that little tiny pink dot right there, I don't know if you can even see that or not. That is the Rosette Nebula. And
you can see that a lot better.
Oh, yeah. We've seen M42, the Great Orion Nebula. We've seen the Flame Nebula there and the Horsehead right there. And I think I'm going to hand it over to Mark now.
All right. Well, thank you very much, Daryl. It's wonderful. I like listening to that. That's why he's an astronomer guy, because he shares things that I wouldn't necessarily think about, and I love it. But I do want to share again. I want to share a few things right now. He mentioned the Rosette Nebula. Well, this is the Rosette Nebula right here.
Yep.
Right. This is
my new
beautiful. Yeah.
So pretty.
This is the deepest shot we've ever taken of it, and I believe this was a 45-second shot.
Wow.
Now, in order to get it as clear and noise-free, we took a number of 45-second shots, and we actually ended up, making them. We stack them on top of each other. All right. So by making this image stack, all the dark detail comes to the top, and the noise in between, which doesn't belong there, is averaged out and goes away. So the more of those you take, to a certain extent, it makes it beautiful. So this is what we got here. And if we actually close in, let me just close in on it a little bit. Okay. All right. You'll notice that there are a bunch of little objects in here. Like, let me go back to full screen here for a minute. Okay. Right here. Okay. These objects right here that you're seeing.
Are those Bach globules?
Yes, they are. These are Bach globules. Very good, Tara.
Okay.
Yeah. These are areas where we see these self-condensing gravitational clouds of dark dust and gas. Everything you see that's orange in here is hydrogen gas. And it's because hydrogen is the most abundant element in the entire universe. Hydrogen is, and that's the number one abundance. Number 2 is helium. Number 3 is oxygen, believe it or not. And number 4 is carbon, which makes us. So the likelihood of carbon-based life out there is probably pretty high. I am a carbon bigot. Yes, I am. Okay. But as Tara said, these are Bach globules, and these globules will be potentially, most likely, the site of a new star at some point. We're watching them condense right here, right? Or they may be the site of a new star plus a planet, a planetary system that may form in there. So we have a lot going on in here. All right. And then if we move over, you see here's a young cluster of stars that formed the Rosette Nebula, and it formed inside of a tumultuous collection of gas and dust. Here's more dust over here. Okay. You see more dark lanes, more dark dust all throughout. But the stars do something interesting. Look at this. They hollow out a cavity inside of here. Now, these are big, massive stars, young stars. They have very, very strong stellar winds. These stellar winds blow this stuff out at a very, very high rate of speed, and they make it so that these objects will hollow out the cavity inside of the cluster. And this cluster cavity is something that's really, really very special, because when we look at it, you can see the hollowed out interior. That hollowed out interior here, okay, is something that is expanding. It's being pushed out more and more and more. Over time, it's going to get more large. And the time will also come where these stars will stop being able to produce as much stellar winds and ultraviolet energy, which ionizes this hydrogen, which is why it glows orange. Okay, it's a glow. It's not a reflection. Okay, it's a glow induced by high energy light. Okay, and so when we look at that, eventually this will fade away because this material will be pushed out. The material that's out here, there might be more hydrogen out here, but you don't see it glowing. Why? Because very likely it's reached the ionization radius, the limit to which these stars can ionize that hydrogen. This is light years across. So these hot young stars can ionize for light years.
Mark, I have a question.
Yeah.
We may have touched on this during a recent live stream. I believe the rosette is at a similar, if not the same distance as Orion, the molecular cloud in Orion.
Yeah.
Are they? They're next to each other in the sky. Okay. I mean, there's Orion, then Monoceros, the unicorn, sits just to the east of it. Are the clouds contiguous, or I guess are they part of the same big molecular cloud?
Good question. I'm wondering. It's possible, but I don't know. I'll have to check. I know that it is close to the other Orion molecular cloud complex, but I don't know. In fact, I mean, I don't think that the rosette's farther away, okay, than the Orion molecular cloud, right? The rosette is like over 5,000 light years away, whereas the Orion molecular cloud, we're talking about 1,500 light years or so.
Yeah.
So I don't think that they're, I mean, if they could be contiguous if you think of it in 3 dimensions, right? But maybe they are. As an example, when we look at the Pleiades, you see the Pleiades under a very, very, very nice deep exposure. You'll see the Pleiades will have a blue glow around their stars. And that blue glow of the Pleiades is dust. That dust in the Pleiades is something that is created by the fact that the starlight is blue and the star's light is being ionized. It's being scattered by the dust in these clouds. And so just like our blue sky, we're seeing light that is being scattered, and that the higher frequencies, the blue light, is scattered more easily than other types of light.
I know.
So,
the rosette is a stellar nursery, just like M42 and Orion is a stellar nursery, and M16, the Eagle Nebula, is a stellar nursery.
Yeah.
We see oxygen 3 green light in Orion. Why don't we see it in the rosette? Because it's younger? It's only got hydrogen so far? Has it manufactured oxygen?
No, not necessarily. Okay, because the stars were made with whatever material they have. That oxygen never gets out unless they go supernova. And in the Orion region, we're seeing a region that has had many supernovae occur in that area. So there's a lot of oxygen left over from other processes. Barnard's Loop in Orion, a big, giant, overarching loop around the whole constellation practically, is an ancient supernova, as you yourself have pointed out too, Daryl.
Well, and that's why I asked if the rosette is younger. That, it hasn't had the supernovas to make the oxygen yet.
Well, certainly the young cluster is young, and that's correct. That's right. So it may not have. I'll show you another one. This here, we talked about the Pleiades. Here's the Pleiades taken by Skytor Livestream. This, I believe, was about a 20-second exposure. But look at all that dust. Now, what's interesting about this dust, right, is that we may also be in the same dust as the Pleiades. because the Pleiades are about 400 light years away or so, and we might actually be in the same dust cloud that the Pleiades are currently traveling through. So that's kind of interesting to consider that possibility. So, I mean, when you look at the universe, you think, wow, that's really far away. Is it, though? We might be part of the same family and not even know it. Give you an example. Our sun was born in a cloud of dark nebulae. Dark nebulae, much like this cloud right here, or the iris, okay? That cloud you see right there, all right, over there, just below my finger there, all that out there, that brown stuff, that is a cloud of dark dust. And this is my hot button. These regions in space are the things that I absolutely love. Okay, besides exoplanets, that's another specialty. But these dark, dusty areas, that's where life could possibly form based on the fact that a young star might form in there and that a planetary system could form in there. Going back to this Iris Nebula, why is it called the Iris? Because right at the top there, you see this blue section. Well, that blue section happens to be an area where a star formed. And that star is immersed in this dark, well, what was previously dark dust. And it is now sending its light out, and the dust in this nebula is scattering the blue light from the star. Well, we have a lot of blue light in our spectrum of our sun. Okay. This star might be a younger and hotter star, but it still has blue light, just like our sun does. And just like even stars that are toward the red end of the spectrum will have some blue light in them, just not a lot. All right. And that could create what is called a reflection nebula in astronomy. That's what the blue nebula we see right there is. That's the reflection nebula over there. And that reflection nebula indicates a place where a star winked on at some point in the past. And that winking on created this visible nebula. Now, even if this star wasn't there, it's possible that other stars in the area might have illuminated this dust enough for us to see it. But certainly, this star that's illuminated the nebula near it like this in the way that it does, certainly that's also something that has been done before. Okay. And, that process of lighting up that nebula is one that is throughout the universe. We see it everywhere in the universe. Okay. I'll give you another example of where we've seen that. All right. I'm going to show you right here. I'm going to come back out now and go to another object that we took the other night. And that was a nebula called the Embryo Nebula. Do you remember that?
Oh, yeah.
Oh, yeah. The Embryo Nebula was really cool. And, the embryo is very interesting because it's also an area that's replete with these beautiful dark dust and everything. But check it out. There's the Embryo Nebula. Notice that it actually looks like the iris to some extent with modifications. Okay. If this is the iris, okay, you see that blue reflection nebula
right,
with the brown dust. Now you come back and look at the embryo, very different part of the sky, and look what we got. We have the same kind of thing where stars winked on and their light is being scattered by this brown dust, which are these little micron-sized particles of dust that may have ice on them and everything of different kinds. And then within this, we also have hydrogen gas, and some other stars in here were hot enough to cause the hydrogen gas to glow and make what's called an H2 region or a hydrogen alpha region. And so this is also a stellar nursery, which is also sporting a beautiful reflection nebula. Down to the lower right, we have another one, a reflection nebula, and a stellar nursery that is got at least one hydrogen alpha cloud in it right now. Maybe this is what this looked like some point in the past. We don't know. Maybe there's another star in here. Maybe one of these stars is illuminating or causing the hydrogen gas to glow. I suspect it's another star in here because there's also hydrogen in here that we do not see. Right? So this star may not be sending out enough ultraviolet light. It could be sending out blue light, but not possibly ultraviolet in the very high energy end of the spectrum, which is required to ionize hydrogen. But that's the Embryo Nebula. And that's in the same kind of region of the sky right there. right? So that said, we also we're looking at a couple of other really cool objects right near Orion. In Orion is actually an object called the Horsehead Nebula, and if you see Orion's belt, okay, Orion's belt is really, really cool. It has those 3 stars. You have Alnatak on the left. Okay, let me do it this way. Yeah, like here. Okay, Alnatak, Alnilam, and Mintaka in the belt of 3 right there. Okay, so that's the belt we have in Orion. Alnatak, Alnilam, and Mintaka. Well, Alnatak, all right, is this star that you see just over there. Okay, it's actually right here. This is Alnatak right here. All right, and Al Nalam is just out of view up by the G in KGRA, just above the G in KGRA up there is Al Nalam. And then Mintaka is further up by about the same distance from there to here. So that's how big our view is. It's 4 full moons across and 3 full moons tall. And this is the special object called the Horsehead Nebula. This is a neat nebula because when we look at this nebula, all right, move over to it. All right. It certainly does look like a horse. All right. And the Horsehead Nebula is a dark nebula. It's part of the Orion Molecular Cloud Complex, the OMCC. And you can clearly see by looking here, all right, and this, you can see this dark shroud of dust. This is not all there is to the Orion Molecular Cloud. The Orion Molecular Cloud is massive. Many tens of degrees across the sky it travels and moves, or spreads, I should say. And you can see also that somewhere in here is also hydrogen that's being forced to glow. Now, if we come up here, Alnatak is responsible for, and Alnatak is a hot O-type star. That's the hottest and bluest there are, and they have much of their radiation being given off in the ultraviolet, the very high energy end of the spectrum. You'd get a tan so fast here that it'd go all the way through all your layers of skin before you went, what? So in other words, you'd be fried to a cinder. So let's stay away from Alnatak. But Alnatak is also a very young star. It's only a few million years old, and it's only going to last a few more million years. And then what will be here in its place will be a supernova remnant eventually, because it's going to go boom. And I just want to see that. I just do. You know, I haven't seen a supernova up close. Not anyone. No one actually in humanity really has. Okay, this would be considered a very close supernova. Nothing that could hurt us in any way, shape, or form. But boy, wouldn't it be fun to watch it expand in the sky?
Heck yeah.
It would take years to see it, but we'd watch it. We would certainly watch it.
And it's the stars blowing like this that produced Barnard's Loop.
Yes, that's right. Barnard's Loop is, like I said, it's the whole constellation of Orion. It's a big arching. You have Betelgeuse, you have Bellatrix, you have Rigel. Okay, Rigel here, and Scythe. I got it backwards, but in the belt of 3, and Barnard's Loop goes all the way around the outside. It's literally massive. So it's been there for many thousands of years or more, tens of thousands of years. I'm not sure the actual age, maybe even longer than that. I haven't looked it up, but you know, I memorize processes, not years and dates and things like that. But inside this here's another example. These 2 stars are scattering the blue light, this cloud is scattering the blue light from these stars that are in here. And this is dark dust. Now, there's probably hydrogen in here. You can see some pinkish glow inside, and that's probably due to hydrogen gas being forced to glow in the same way. But if we come down here a little more, and we look at this edge right here, right along the horse's head here, this edge is a beautiful wall, an edge to the molecular cloud. And you'll notice that there's fewer stars here and more stars over here. That's because there's a lot of dark dust in here that's blocking stars behind, and also some of these stars can be embedded and or in front of this dark cloud. But over here is Sigma Orionis. This is a star system that consists of at least 6 components. And they're all gravitationally bound to each other, it appears. And this, again, born in a stellar nursery that dissipated over time, But however, it's causing this entire wall to glow because it's ionizing the hydrogen. And the way that works, real simple, hydrogen has one proton and one electron. And when you actually go into a hydrogen atom with energy, the electron feels the brunt of it. The electron goes to higher and higher orbital levels, okay, until finally it leaves the atom. That's called ionization. All right, so it's gained a lot of energy to do that. So there's all this energy spinning around out there. But as it spins around out there and moves around out there, it's going to collide with other things outside the atom. And that's going to start causing it to lose energy. So it eventually comes back down, gets pulled back into the atom. As it gets pulled back into the atom, it cascades, dynamically down multiple energy steps. They're actually fairly discrete, which gives rise to the study of quantum mechanics. Quantum are discrete levels. And so quantum mechanics are the discrete levels within an atom. That's where this all started. So as it drops down, they drop down to many levels and give off light as they do. Every time they drop down a level, they give off light. So if it drops to n equals 4, gives off light. N equals 3, gives off light. N equals 2, gives off light. But in general, most of the drops occur down to the n equals 2 level. And that gives off light that is characteristically red, like we see here. And so that's why when we talk about hydrogen 2, okay, it's basically singly ionized hydrogen. You can't have doubly ionized hydrogen because it only has one electron. Okay, and that's a Roman numeral 2. And the Roman numeral 2 is because the 1 is not written all the time, but it's present when an atom has all of its electrons. It's not ionized. It's in its base or ground state. That's like calcium 1 is a calcium atom. Hydrogen 1 is a regular hydrogen atom. Helium 1, regular helium atom. But we don't say that because it's sort of redundant. It's understood. So,
may I
yes?
chime in here?
Yeah.
You can go up to Alnitak and the Flame Nebula if you want to. As Mark said earlier, Alnitak, the bright star there, is lighting up the Flame Nebula. Plus, there is also a cluster of stars inside the nebula. But Alnitak is doing most of the work here to illuminate and excite the Flame Nebula. And then going back down to the Horsehead and Sigma Orion over there on the lower right, Sigma is illuminating and energizing, ionizing all the hydrogen there in the wall, which we're seeing edge on behind the Horsehead. And Sigma is absolutely beautiful to look at in the eyepiece.
Oh, yeah.
As Mark said, it's like 6 stars or more all orbiting together. And it's very close. You have to have some focal length to break them down. But Sigma Orionis is absolutely gorgeous to look at it in an eyepiece because you can actually see the stars.
Yeah, and it is true. It's one of Daryl's favorite stars. Yeah, mine is Alberio, and Sigma is my number 2. Alberio is the head of the swan in Cygnus. Beautiful, beautiful, beautiful stars.
That's all I wanted to add.
All right. Well, there you go. That's actually the Horsehead region, and again, this dark nebula here, we call it dark nebula because, of course, it's dark. Not the same as dark matter, not the same as dark energy. The word dark in those terms just means misunderstood, not understood, right? So, but dark nebula, dark because it's made mostly of carbon and silicon grains. So you can see that a carbon molecule, 2 carbons, carbon, is going to be 2 carbons together to make 1 molecule of carbon, of carbon atoms, and that is going to be, of course, black. All right, and that's like soot. And that's the stuff that was made in some of these stars that are what are called asymptotic giant branch stars. All right, we talked about those last week. Star uses up its hydrogen, turns into a red giant, then starts burning helium and goes down a horizontal path, and then comes back after it starts growing again and becomes a red giant for a second time. And it's during that phase that these things called dredge-ups occur, and we can get a lot of carbon that's in the star's atmosphere brought to the surface. Now, these are carbon nuclei, but when they get out to the outer atmosphere of these red giants, well, electrons can recombine with them, and now you have carbon atoms, and then the carbon atoms can combine and become carbon molecules way, way in the outside atmosphere of a massive red giant. And that's something that we see. We see what are called carbon stars quite a bit, right? And these carbon stars are, in fact, extremely red. They're so red that you honestly you can't get over how red they are. But I'm going to show you because I have one. Let me show you. All right. So, all right, this is an example of a carbon star, right? That guy right there. This is called WZ Cassiopeia. All right. It is a carbon star. Now, if I did a shorter exposure, this star would have looked absolutely crimson. It would have been just beautiful red. All right. The star is a giant, super giant star because the carbon stars are going to be these very, very, very big stars with distended atmospheres. And this one, again, is in Cassiopeia, where we looked the other night. Okay. And so WZ Cass is what we call a carbon star. And the carbon comes up to the upper atmosphere. And because the star is so distended, and because this carbon molecules are made out there, it's like a star having soot, okay, from a fire, essentially, right? Soot, carbon molecules in its outer atmosphere. And it makes the atmosphere look redder and dirtier. And so that's why we get these stars with this type of look to them. Carbon stars are absolutely stunning to see in the eyepiece or in the telescope cameras. So that's something to look forward to. We'll do more of those moving forward as well. Now, in addition to the carbon stars, we have been able to do other things. Like we talked about massive stars, when they explode, well, they create supernovae, right? Well, we're going to talk a little bit about that. We're supposed to get more into it, but I want to also hear from Tara down there because she's got some really cool questions tonight. But this is an example of what it looks like if we have a supernova. Now, one of the things that I did was I put up one half. This is called the Western Veil, right? It's a Veil supernova remnant. It's about 8,000 years old, actually. And it's about 1,500 light years away, about the distance of the Orion Nebula. And at the other side, we have the Eastern Veil. All right. Now, when you look at these, and you look at them separately, they're really not very impressive. It doesn't look that impressive. But what looks impressive is when you look at the entire conglomeration, and this is what you see. This here, this is the whole veil. So this is the whole supernova remnant. The star that caused this is somewhere in here, right? The progenitor. It's actually not been really truly identified yet. They think it's called Cygnus X5, okay? And it's a soft X-ray, has X-rays that's given out. They think that might be the source. And this is several light years across. So that means that the star blew up and that material has been moving out ever since. And there's not very much to stop it except other stuff in the interstellar medium. Now, Daryl will say when we look at this at night that this looks like a face over here with a nose and a mouth, right?
Oh, yeah.
Yeah. And this is known as the witch's broom. It kind of looks like a witch's broom. My pretty. Yeah. But this is a beautiful picture that we obtained of this. And it's in the constellation Cygnus, which is a summer constellation. But I wanted you to see how much, a supernova remnant can spew out there. Because the green here, this is ionized oxygen, doubly ionized oxygen, in fact. And we call it O3 because O1, Roman numeral 1, is the base value where it has all its electrons in the oxygen atom. O2 is a singly ionized, that's OII, the O Roman numeral 2, singly ionized. And O3, Roman numeral 3, is the doubly ionized oxygen atom. And when those electrons come back in, they go to a predominant location, which gives off mostly this greenish blue light. And so that's what we see. The red is mostly hydrogen. Now, it stands to reason that's the case, because hydrogen is the most abundant element in the universe, as I said. Oxygen is the third most abundant element in the universe, and helium is in between them. So we have hydrogen and oxygen in this list. It's like, what am I doing? Like some kind of heavy metal thing. So that's what that looks like, and that's just a beautiful supernova remnant. All right. So what I'd like to do is have Tara give us some questions that we can talk about. I know she's been chomping at the bit to do this. You can tell. Look at her. She knows she wants to do this. Look at her.
I think it's so interesting just to listen to you guys talk. I just learned so much. And
yes, but you somehow have to pay for the rent of your space on the screen, so you got to talk to us now.
Okay, well, let's talk about large and small numbers in the universe. And
right.
Because that's the big issue, right? Is how do we understand and comprehend this? And I'm wondering if you might be able to help us understand, Mark, about how it's hard or even possible for us to imagine 1,000,000 of anything or 1,000 of anything, and how can we relate to the stars with those? Does that make sense?
It does, and I think I know a book you probably read that
did.
You some ideas.
Yeah,
about that.
because you talk about that in your book about the largeness and the scale of the universe, and how do we know that these giant stars are also bigger than the sun, and all that. There's so many questions.
Yeah, let's go back to just the sheer numbers, right? In the book I wrote called The Populated Universe, the first chapter is called The Problem with the Numbers, and it talks about there being a problem with our number systems. If you try to make a model of the universe or just the Earth-Moon system, if you want to accurately portray anything, the numbers quickly get astronomical. Let's say the solar system you want to make. I used to actually do this. I would take people outside, okay, and I'd say, we're going to make a model of the solar system. I had sticks with planets on them. I said, okay, you're going to be the sun, and the sun is going to be 2 feet in diameter. Okay, now I had people, we went on a football field, so you kind of get an idea where this is going. Okay, in the far end of one end zone, and I don't think it wasn't a beach ball. It was actually like a play ball, and so certain size play ball that I had, that they had in the gym, and then they had the rest of mine. And we started with Mercury, Venus, and Earth, and they said, oh, well, that's not too bad. Okay, Earth is going to be like 12 or 14 feet from the sun. Yeah, we're fine with that. I can see the sun and all that. Then you get to Mars, and now you're like, whoa, we're like 35 feet from this ball now. And then you go to Jupiter, and you've got to run all the way downfield, okay, and get out to like 100 feet or more. And I got the numbers wrong. I have it all written down somewhere. But the bottom line is that Pluto, if you go to Pluto, it's all the way, I made it for like a football field. It's all the way in the opposite end zone. And it kind of gives you an idea of why it took 15 years to get all the way out to Pluto with the New Horizons space probe. You also get an idea why it would take many years to travel across the face of some of the largest stars in the universe. Just to go across the face of the stars would take many years, okay? Because some of them are bigger than Jupiter's orbit, all right? And that's on both sides, remember. It's all the way from the end zone of one all the way out to, 100 feet or more to Jupiter, and in the opposite direction too, right? And now that has to be a sphere, a big sphere. And the sun is this big. So we have a very moderate, we're a moderately sized star. We're not big, we're not small. We're right there in the middle. And the biggest stars make ours look like the tiniest pebble on the sand of a beach, right? So the numbers, if you want to talk about them, they quickly get astronomical. When you're a child, you're in a playpen. Your world is the playpen. The walls of the playpen are the end of the universe for you. As you get older, you're in a crib. All right. And say you look out of the bars and you can see out the window of the house. Well, now your universe is as far as your eyes can see outside the crib bars, but your universe is defined by the crib bars. Then you get old enough as a toddler that you're in the house looking through the front door. The house is your universe. The door is the end of the universe for you, but you look out there and you see there's more out there, right? So, in the same way, it happened with us. We thought that the stars were all in a sphere around the Earth in the firmament.
A firmament, yes. Mm-hmm.
Right? And yeah, as astronomer Nichols writes in the Architecture of the Heavens in a series of letters to a lady, which I have right here, published in the 1800s about the universe before they knew much of anything about it. And so from that, Edwin Hubble in the late 20s did a study of these island universes in the sky, as he termed them, these nebulae, spiral nebulae with spiral arms, and determined that they're actually all their own. They were on their own. They were doing their own thing. They were these galaxies, and that maybe we were seeing galaxies beyond our own, and that increased the size of our universe, and it's been increasing ever since. Right now, we see out visually. We can see out about 13.6 or so billion light years, which corresponds to about 13.6 billion years ago. We can't see all the way to 13.8, okay, because of the cosmic microwave background is as far out as we can see. However, that's not the size of the universe. It seems it, but that's only 13.8 billion years, Tara. 13.8 billion light years. The universe is 92 billion light years in diameter. Okay, because it took 13.8 billion years for all that light to reach us. But in that time, the universe has been expanding outward. And as it turns out, accelerating as it expands outward. Okay, so that means that the universe has grown quite large in the time it took for that first bit of light to get to us from 13.8 billion years ago. So you see, the numbers just rise and rise and rise. And it's like we talked about the Kelvin scale. Remember, we needed to have a scale that would make sense for us to calculate. I mean, here it is again, right? Right. Kelvin degrees, 0 degrees Kelvin is minus 460 Fahrenheit.
Nothing colder than that, right?
Yeah, that's correct. You can't have a -1 Kelvin. Okay. 100 Kelvin is minus 280 Fahrenheit. Okay. The moon at its coldest, right? That's minus 173 Celsius. Right? The boiling point of water is 273.15 Kelvin, or 0 Celsius, 32 Fahrenheit. So it's all a matter of scales, but we create these different scales in order to be able to make sense of the universe. And we needed Kelvin because Celsius and Fahrenheit were based on the freezing point of water. Well, that doesn't work very well scientifically if we're studying cold, dark clouds of dust out in space, right? I mean, we'd be still talking about minus 200 degree temperatures Fahrenheit on the moon, where it's pretty cold. Minus 280 is about as cold as it gets on the moon.
It's freezing.
Yeah, that's pretty cold. All right, but that's about 100 Kelvin or so. So we're talking about a very different paradigm. Daryl, I don't know if you want to throw in anything about this with their question.
Oh, the scale you just showed, Fahrenheit, Celsius, and Kelvin. I have seen that expressed in other ways. There's a fairly well-known diagram out there, and how to put it? Fahrenheit and Celsius from boiling to 0. At 0 Fahrenheit, it's really cold. At 0 Celsius, you're really cold. At 0 K, that's as cold as it could be. The point was at Fahrenheit, at 100 Fahrenheit, you're alive. At 100 Celsius, you're dead. At 100 Kelvin, you're dead at both the top and the bottom of the scale.
Wow.
That's an interesting observation.
Yeah,
Yeah.
If I can find it, I'll send it to you.
Okay.
that's very cool.
Does that help
Uh,
you, Tara?
beyond that,
Yeah,
Okay.
go
Go ahead,
ahead.
Daryl.
beyond that though, we're monkeys at heart, and we hold our hand out in front of us. Well, we can count to five, and if it's more than five, all of a sudden it's become a bunch.
Yeah.
And you've talked before about people not really being able to comprehend big numbers.
Yeah.
I like to think I can visualize 1,000. That's just if you make a row of 10 and you make 10 rows, 10 columns, and then you make that
Yeah,
that 10 high, that's 1,000, just 10 by 10 by 10. But beyond that, all of a sudden, it gets to where the numbers are meaningless to you.
It's unwieldy. Yeah.
yeah.
Yeah,
Your eyes start glazing over, and
That's right.
yeah.
Now, Daryl mentioned monkeys, so it just stands to reason I would put up the monkey head nebula that we took the other night.
oh,
That's the
cool.
monkey head.
There you go.
Yeah. And monkey head again. Uh, hydrogen emission region here. You can see this dark dust cloud overlapping into this area. That's not void in the space. That's actually a dark dust cloud, which you can see much of it here. Okay. Which is actually really cool. Let's do this.
Where's the monkey head in it?
Well, you know what?
I really don't see it.
It depends. I think this is one of the eyes. This is another one of the eyes, and this is the mouth here, part of the mouth. This
Uh,
might be the face
Oh,
and the
maybe a
ears.
side kind of.
it's
Okay.
Ears.
Oh,
it's overexposed.
It is.
Yeah,
it's like his
the
face.
eye is actually just to the left of where your pointer is right now.
This one, right?
Yeah, no, not that. To the upper left there.
Well, I guess the upper left up here.
Excuse me, to the upper right.
You mean this one?
About that area there. On a shorter exposure, that's a dark area. That makes the
Oh,
monkey's eye, and then his nose is below that, and the curved horizontal line toward the bottom is his mouth. It's overexposed to the point you can't really see the monkey's head anymore.
Well, I mean, I can see like an ear, another ear, an eye, a round chin, a nose,
yeah.
and a mouth.
Yeah, when we did this the other night
Yeah.
on live stream, when you first saw it was pretty obvious. It's the time exposure is built up to the point where you can't really see the monkey's head now.
Yeah. All right.
We're about
That's
to
pretty
run out
cool.
of time.
Got 2 minutes left, about or
Yeah.
less than.
So give us one more question, Tara.
Oh my gosh. Can binary systems have planets between the stars? Can there
Yes.
be a star like in Jupiter's orbit if it were ours?
Yes, and we're out of time. No, I'm just kidding. It's possible, but the planet would most likely be a very, very hyperinflated planet, a very
Because they're so close. Oh,
bloated planet, a gas giant. It wouldn't be a livable, habitable world in any way. And it would probably be unstable. Depends how far the stars are away from each other.
right.
So you could have one star orbiting another star, and then within that, you have another planet orbiting that other star as well, possibly. But that planet would be influenced by the gravity of this other star. If this is a low mass star, it might survive for a while. If it was a high mass star, it probably wouldn't survive for long and would have long since, unless we find it happening now, long since been disturbed in its orbit enough to be spiraled out into one of the other stars.
Very
We
cool.
are out of time.
Out of time. Thank
Yep.
you.
Well, guys, thank you so much for joining us for another edition of SkyTour Radio. We will try to be back next week. We'll let you know along the way. And it's clear out there in Arizona, and we may be streaming right after this, Daryl. So,
You maybe, not me.
all right. I will.
Well,
Okay, guys. We'll see you later. Thank you for attending to us, and we'll see you next week.
good night.